Hello, my name is Stuart Dixon, and I'm a zoetrope guy. I want to tell you about my adventures with the famous Calabi Manifold picture from 1990. It's taken on a life of its own. In 1990, I was working on images for the second edition of Stephen Wolfram's Mathematica, a system for doing mathematics by computer, which was known as the Mathematica book. It was essentially the reference guide for the software. There's a professor of computer science at Indiana University named Andrew Hansen. He had some mathematics relating to visualization of Fermat's last theorem, which he couldn't get to produce any graphics on any hardware he had available to him in 1990. I could do it on a Silicon Graphics Personal Iris. It's an R3000 Personal Iris. It worked just great. So what about Fermat's last theorem? It's fairly simple. It's an extension of that Pythagoras theorem doesn't work for exponents greater than 2. Um, and this was an unsolved problem for almost 300 or a little over 300 years, like 360 years, right? Unsolved. But this guy announced a proof of the Taniyama-Weil conjecture, which uh, relates to collections of elliptic curves, sets of elliptic curves, which implies the proof of Fermat. This was like his last sentence, uh, uh, um, presenting his proof of the Taniyama-Weil conjecture. Implies proof of Fermat, which was unsolved for 360 years. Turns out that the only available image visualizing the mathematics was my picture. So it like wound up in the New York Times. Here are the mathematics of Andy Hansen's visualization of Fermat surfaces for any exponent n and any rotation in the complex plane. As you can view in the Wolfram demonstrations project, like here, this is the n equals 5 version. Andy Hansen's parameterization of the Fermat surfaces contains n squared parametric surface patches, and the n equals 5 case parameterized in 2 complex dimensions yields a 10-dimensional structure as in string theory. So when Brian Greene came out with the Elegant Universe in 2000, Andy Hansen had his graphics working, so his versions of the visualizations ended up in the book, but my picture made the cover of a 2017 Folio Society reprinting of the book. And there it is. In 2005, a proposal for a 4D zoetrope of the Calabi-Yau manifold rotating in complex force space was published as an artist's note in Leonardo, the Journal of the International Society for Arts, Sciences, and Technology. The zoetrope itself was 3D printed in Western North Carolina, and it was constructed with the help of a WNC Media Arts Project grant from Asheville, North Carolina. It was exhibited in a little art gallery. I don't remember the town. It was just down the I-27 from or is it I-23? I don't remember, from Asheville. Little gallery down in southwestern North Carolina. Here is a flip booklet of the Calabi-Yau manifold rotating in complex force space. Imagine my surprise when Mark Rober's Crunch Labs came out with Build Box number 6 about a year ago. 2023, the strobe light animator. That's a zoetrope. Look at the little animated tiles in there. They're laser cut, laser engraved. Laser cutters are like makerspace things. So I went down to Chimera Art Space in Sebastopol, California, and made a set of laser cut replacement tiles for Mark Rober's Crunch Labs Build Box number 6 strobe light animator. They're mathematically themed. Here's the metamorphosis. It's a torus opening up into Costa's minimal surface. And here is the Calabi manifold from string theory rotating in complex force space. Here is Chimera Art Space, the exterior, Sebastopol, California on Route 12, on the way from Santa Rosa to the beach Santa Rosa to Bodega Bay, which is this big tourist resort place. There might be a beach in Bodega Bay. Mostly it's yachting, I think. And here's the laser cutter inside of Chimera Art Space. And it's probably working on animation tiles for Mark Rober's Build Box number 6. Uh-oh, what's this? It's a big movie. Little movie that is computationally heavy. I wonder if you show the cursor in Apple screen capture, do you get to record the beach ball rotating? I have to try that. I don't know. I don't know the answer. We'll just wait for this thing to load, I think, because it shouldn't take too long. It's a fairly beefy computer. It's like 16 gigabytes or something. Maybe it's not that beefy. Okay. Yeah, that really is a fairly low res movie, I think. I wonder why it's so heavy from the computer's point of view. This thing's supposed to be playing back. Oh well, anyway, it's the animation tiles inside of build box number 6. It's supposed to be animating. And here is the build box with the things open. This is actually the heavier movie. I wonder if we back it up, if it'll play. Oh, there it is. Wow, funky. Well, frame rate's a little high, but there we are. There you have it. That's my story. Thanks for watching.